Good morning, calculus.
Good morning.
Thank you for showing up face to face, Adrian McKellar. So I've got a test to grade for you guys. I had a hectic day that went till 8:30 last night, so I didn't get it yesterday. But after I get out of class today, I will get that done, and I'll have it for you before today is over, unless something terrible happens. Um, so I usually make it a point to grade them the same day I get them. So I apologize for that, but it's not far behind. I might quickly, just because I graded this the other day, quickly want to show you this. Many of you got it right, but I just want to show it to you quickly because I think it'll help it sink in a little bit. I won't necessarily do everything, but I'll at least show you the short answer. So with respect to this question, I did not tell you much. I mean, I just drew the drawing and said, go find it surface area and volume. So let's do volume first. But one of the things, in order for the points that pertain to presentation, as I said out loud, I'm not necessarily looking for you to, type it all up and make it super fancy. Although if you want to do that, awesome. And some of you did that, and that's really cool. But sometimes, just the ability to make something look good when you should, I think is kind of cool. But one of the things you would need to tell your reader, because a lot of you jumped right into this and just assumed a lot of things, but you got to you have to choose your axis. Like, you definitely needed to tell me that, maybe that was going to be your XY axis. So lots of you didn't tell me that. And again, it's not so much me, but it's your reader. If you give the equation for that circle over there, that's a meaningless statement unless you tell your reader where your XY axis was. So that's important. And then also, are you going to rotate it around the y-axis? And many of you just assume that because of the way that I drew it here. It's very natural just to pick your axis as either this up here or the one down at the bottom and see it as rotating around the y. And so you could assume that for sure. Not everybody did. Some people rotated it around the x-axis. But you got to say that. You got to at least kind of point that out to your reader. They're not going to understand what you're talking about. So all I'm seeing, and I don't do this very often, but it's like, there's a time to think, I'm going to communicate this to people. There's like things they got to know to be able to understand this.
If you rotated around the x-axis, wouldn't it make a completely different shape, though?
Not if you turned it. In other words, you'd have to.
Oh, I see what you're saying.
So there's. I didn't put this on an axis again because it's drawn the way it is. It makes sense just to leave it the way it is, but that was never assumed. Had I drawn it vertically, just as a for instance, probably everyone would have rotated around the x-axis, but there's nothing saying that had to happen. So quickly, many of you figured out that relatively quickly that this is a circle, which is x squared plus y squared equals the radius squared. But since the center point of this circle is over here, that ends up, because this is a distance of 4, since the radius of the circle is 4, and you're told this distance is 5 and this distance is 2, then that's a distance of 7. So in the end, your circle has got to slide right 7 and slide up 4. So that's really the equation for your circle. And it's just good to see this stuff in action. That's why I think this is a good problem, because it's like many shapes are made with a curve in them like this. So your ability to define that as a circle and be able to dredge that up, even if you look that up on the internet, so to speak, because it's not fresh in your mind. And then if I solve that, I'll just make this kind of messy because I want to go quick. But if I solve that for y, I'd have to take 16 and subtract x minus 7 squared first from both sides, then square root all of that to get rid of the squared, and then finally add 4 to both sides. And so that's what y would be equal to. But again, there's something not obvious that happens there too that you need to figure out, because when you took the square root of that, given that it's positive, if you were to graph this, actually what you got is the top half of the circle over here, not the bottom half. And so in the end, you got to consider that as the negative of that square root in order for it to be the bottom half of the circle. Again, all these things are not obvious. Awesome. And just so it looks nicer, I'm going to rewrite it as 4 minus, let's see, x minus 7 squared is minus 14x plus 49. So 16. So I end up with inside the square root then an x squared. But I guess that's going to be negative. So I end up with, is it all negatives inside there? I guess so. So this minus sign outside is going to change every answer that I got up here into negatives. So that'd be a negative 49 and a positive 16, which is negative 33. I think that's right. So in a sense, that's the bottom half of the equation of that circle. So and also as far as communication, I mean, you're finding volume and surface area. Did you make it really obvious to somebody that what your volume calculation was? And then thirdly, did you tell your reader whether you're using washers or shells for this as a method? Did you tell your reader that, or did you just get into it? Again, that's the part of communication. I mean, do you stop and notice those things? I was pretty friendly with that. Lots of you did none of what I just said, but I didn't say 0 for presentation as a result of that. I took a point or 2 off for that, but I want you just to think about that. So there's no way to get this in, and this was a discovery that you would have made too. There's no way to get this entire area all in one pass. Well, depends on what method you use. I was going to use shells, but I guess since most of you used washers, I think I'll do it that way. So you would need to explain to somebody that you're going to use the washer method, and then your washers are this way. And again, as I mentioned, I'm going to go, as many of you did, around the y-axis to do this. So that is always the distance of 2, whereas that is the distance of x. And then this thickness right here is a little bit of y. So your integral then would be, since this distance right here is basically x minus 2, or in the end, what you're really doing is finding the volume of the outer washer minus the inner washer. So if I said the outer washer is pi times radius squared times height, that's the outer washer, minus the inner washer, which is pi times radius squared times height. And by the way, there's more than one way you could do this. You could just kind of not worry about that at all. Just let your x distance go all the way to the axis and be done and have this thing be solid. kind of like that. And then come back and just find the area of the cylinder on the inside and then just subtract it later. You don't even have to do the inside cylinder with calculus. So I could save that for later. Most of you did what I did here, so I'm going to leave it in there. So then you could look at that and say, okay, cool, look, they both have a dy, they both have a pi, so I could take a pi outside. And I now see that I'm stuck working with y's since my height was dy, so that means I got to switch out that x for y right there. And I said that you don't actually have to take these integrals because they end up hard to take. So x is replaced with y is my cool statement up there. See that I left out that x up there. So there's my x value, which is now squared, and then there's dy, or I could just wait till later and keep on going and say minus 2 squared dy. And then cheat to get the answer. So after today's project, we're going to discuss, is it possible to take that integral yourself? And the answer is yeah, you got to be better at integrals. And so we're going to tackle that. And then lastly, I just have to say, well, what are my y values? Since I'm working with y's, I need this thing to slide all the way from here. I need that shape to go all the way to the ground and all the way to the top. And since this is a radius of 4, then that's an x coordinate of 4. So it's going to be all the way from 4 to 0. So if you don't blow that, you get 146.83, which many of you did. Very important, cubic centimeters, because these measurements were centimeters. So part of your presentation was units. You can't just say 146 for this. That's a meaningless statement in the real world. Now, what I've written here is not nicely communicated. That's a mess. That's a disaster up there. It'd be much better to have some steps in it. But since we're talking, I can sort of get away with it being messy. Quick look at surface area. So the only thing that took calculus is kind of this outer surface area, those stripes that kind of wrap all the way around that shape. But then, and I won't take the time to do this, but you've also got to find the surface area of the top, which would be the area of a circle minus the area of a circle. That's pretty easy. People didn't have any trouble with that. So I've got that on the top. I've also got that on the bottom, which is the bottom is going to have the same size inner hole, but obviously a much larger kind of an outer hole. And then you've got that lateral area, kind of that area of the inside of the cylinder down there. And so none of those are calculus problems. So let's just look at the kind of the calculus part of this. So what's that outer shape? If I switch to green, well, I've got that distance again, which no different than before is x. That's my radius. And then I've got this distance right here, which is an arc length. So and some of you did a really good job, and you would need to do this of labeling this. Like you said, top, and then you found the area for that, and then you said bottom, and then you found the area for that. I mean, that's like you want to take your reader on that journey a little bit. So what we're doing is just kind of the outside. And you could, of course, label that. You could, aim right at it and say that's area A, something like that. But, make sure your reader can follow that. Some of you did a pretty good job with that. So what is that outside area? Well, it's 2 times pi times radius times the height, which I'll kind of put in quotes because for us, that's an angled height. So for us, that's going to be 2 times pi, which I'll put out in front of the integral, times our radius, which is just x. And since that radius is x, I'd just as soon leave it as x. Therefore, I would prefer to write my integral is 1 plus dy dx inside there, because that leaves dx on the outside, and then I can just work with x's. Now, not all of you did that. You don't have to do that. If you switch this upside down and make it dx dy, so that this is a dy outside, then you just have to replace that x with the big ugly mess that y is. That's totally fine. But I'm in the easiest mode possible here. So here's the things I should have seen. Well, let's see, what x's does this exist for? Well, up here is the shortest x I'm going to get. That's the shortest x, and that's a distance of 2 and a distance of 1, so that's a distance of 3. And then down here it's 7, so that's from x's from 3 to 7, which again, I don't think is obvious. So there's my integral, but now I got to take the derivative of y. So what's the derivative of y? Well, I'm just staring at this statement up here because I don't want to waste too much of our class time today. So let's see, what's the derivative of that? What's y prime, or dy dx? What's the derivative of y with respect to x? Derivative of 4 is nothing. The square root of something is all of that junk raised to the 1/2 power. So if I bring the 1/2 down front and leave all of the junk inside alone, it's a minus 33. And then subtract 1. And then multiply by the derivative of what's inside of that. Derivative of negative x squared would be negative 2x. Derivative of 14x is 14. So there's my derivative, which I now need to square. So to write it a little cleaner, then I guess that would be, well, there's a negative here. I don't really like the negative. I hate negatives. And so if I multiply the negative into this statement, then that becomes 2x minus positive 2x minus 14. There's a 2 on the bottom. And then there's the square root of all that junk. So there's also some algebra here. And so I see I can cancel a 2 out of everything, and then I have to square everything. So dy dx squared, if I cancel the 2 out, would be x minus 7. That would be squared. And then the bottom is really exciting to square because that means the square root goes away. So there's my derivative. So now I can just write out the expression. So I have 2 times pi times from 7 to 3x times the square root of 1 plus, well, there's my derivative. And if I'm cheating, great, type that in my calculator, boom, done. So the overall surface area answer was 383, but just that chunk of it right there is 175, just if you didn't get it right. And this would be square centimeters. The overall answer is 383.2 square centimeters. That's the overall answer. But again, if you want to investigate this further, maybe we'll come back to this. I doubt we will, honestly, but just to point this out, you could actually add these two expressions together, but I'd have to take this one and multiply it top and bottom by that expression right there. And then I could actually multiply x minus 7 squared out and maybe, you know, clean that up a little bit. You know, would that actually go anywhere? Would I actually be able to take this integral myself? Again, this is daunting. But anyway, kind of cool. So anyway, I never want to just give you those without discussing them, because again, my overall goal is that you just learn something from them. Many of you did great, and I'm really glad you all worked together, because I think it helps. I know it's a little awkward because one person that wants a good grade maybe does more work than other people. I realize that whole thing's kind of awkward, but I think the discussion that you have is actually more important than kind of the writing out of it. So I apologize for the negative aspects of working with somebody else. Okay, today we're applying something else, which again, I'm going to do a lot of this with you and for you, because it's just such a cool thing. But I want to take just a second and introduce you to the problem here. So this is something I teach in engineering, and it's these kind of applications that I just never saw, and I just think it's kind of neat to see. So I'm going to go type in retaining wall failures and go to images, and let's just randomly look at some retaining wall failures. There's a major one. So building houses in the hills where you have a view is really cool, unless the dirt that holds the house up is allowed to wash away from underneath the building. I don't know what happened here, earthquake, who knows, but that is not good. Interestingly, that looks like I think that's the same house. So this dude is there filming it apparently when it actually kind of fell. So sometimes it happens because of sinkholes and things of that nature. But this is a common problem that kind of happens all the time. There's a lot more kind of a natural problem. Looks like there's a highway up there or something. I see a guardrail sitting up there. So I don't know what this is, but let's have some green grass down here. But can you appreciate dirt is pushing against that? So today, the title in your syllabus today is hydrostatic pressure, but I actually changed it a little bit. We're going to look at geostatic pressure, like the pressure of dirt against something. But we talked about that the other day. I showed you a problem in the application section of integrals where we looked at, how much force was on that rectangular door at the bottom of a dam. That was hydrostatic pressure. And we talked about the fact that the water backed up against the dam is pushing horizontally. Well, the dirt's doing the same thing. And this is where you can turn a class like this into money, which is ultimately kind of why somebody thinks you should take this class. But it's much harder than taking the integral of x squared plus 2x. As I've told you, no one's ever going to ask you to do that. You got to formulate the integral yourself. And it wasn't until a lot further into my teaching career that I actually saw some of these kinds of applications as a part of the construction work that I do. But that dirt, just like water, is pushing against the wall. And if you don't think that through, it looks like in this case, had they maybe run some rebar down inside this and poured those full of concrete, maybe that would have been able to resist that, maybe tie the wall into the hill some more. Who knows what went wrong there. This is kind of how that's done. And when I say tie rebar in there, this is kind of what I mean. Like you pour concrete, but you got to pour a lot of concrete, really heavy concrete, and you've got to put rebar in it so that the concrete can't get pushed over by the dirt or the water that's pushing against it. But it does push against it. And this seems crazy. I don't know what this is or what country this is in, because again, I'm just clicking on pictures here, but man, that's a really tall wall to be made out of bricks. Bricks do not like to stick together very much, and to expect that to hold something back, man, that's just crazy. So I'm sure you could find all kinds of videos. It looks like this is the same picture. Looks like there was some kind of a road up there. Obviously, this is in a nice neighborhood. This is kind of where the stuff happens. People that have money want to live up on a hill where they have a view. Totally get that. But then when you're driving in hills, you got retaining wall kinds of issues involved. And That just didn't work out so good here. So that looks like a road or something like that. Anyway, let's break it down. So in my open math, there is a project. If you haven't pulled that up, project 5, you pull it up because we're going to look at it now. And all I really want to do is just, just teach you some things about how the world works, open your eyes to some things. My larger concern is like, oh, great. Now it is not, oh, great. Now they can all be engineers. That's not my point. My point is just to get you to think and reason a little bit so you actually understand what an integral can do, so that whatever applications you may run into in your life, and again, there's a really great chance you won't run into any unless you, well, maybe pick engineering as a career. But here's the deal. So I put this simple picture up here. This is what usually happens with retaining walls. There's dirt behind it. Notice that retaining wall is only like 3 feet tall. And notice it isn't catastrophic, like it isn't, falling down the hill and everybody dies, like, the most interesting pictures on the internet. This is just time pushing against that wall, and you can see it's tipped out some. It isn't broken, but it's tipped out there. And so that's your job as an engineer, to keep that from happening. And so, the interesting question is, what does this have to do with an integral? Like, why would an integral be a part of this? Well, here's the basic idea. Can you appreciate that up here, and we talked about this with respect to the water that was on the rectangular door. Does it make sense the dirt that's up here kind of high isn't pushing near as hard because there isn't as much of it as way down here at the bottom? Because down here at the bottom, you got a lot more dirt piled up. And again, it's easier if you think of it as water. And I'll show you that in a minute. But dirt doesn't behave the same way as water. It actually doesn't push quite as hard. But basically, there's a lot more dirt here, 3 more feet of dirt. And so there's a lot more push on the bottom than there is on the top. Does that make sense? So engineers will highlight that by showing you something that looks like this. And I'll show you this in just a second too in the drawing that I made. But they'll show a wall like this, and it'll have like a short arrow, and then a longer arrow, and then a longer arrow, and then an even longer arrow, and so on and so forth, because each force is getting larger and larger. And so the first one might be 10 pounds, and the next one's 20 pounds, the next one's 30 pounds. So it just gets kind of heavier and heavier as you go down. And maybe you understand this, but if you were going to, I'll ask if you do. Let's say there's a box just sitting here on the floor, and you decide you're going to tip it over for whatever reason. Maybe it's just easier for you to work with it laying on its side. If you were going to push on it, where would you push to tip it over? Would you push low or would you push high?
Oh, hi, sorry.
Yeah, perhaps you know that torque equals force times distance. Maybe you've taken some physics. If you haven't, I'm teaching you a little bit of physics right now. So torque is just the desire something has to rotate. And so you only have a certain amount of force in your muscles. Maybe you can push with 100 pounds, and you're going to get more from your 100 pounds if you multiply by a longer distance. So the higher up you push that, the more it's going to want to rotate over. And if you've never played around, like you don't have any spatial physical awareness, go find something in your house and play with that later today. Like just stand the box up and just push really lightly, and you'll notice it tips super easy if you push on the top, but it doesn't if you push on the bottom. And this is what mathematicians do. It's like trying to create like what's causing that to happen. So it's just rather brilliant to me that people, humans, have come up with formulas like that. And so if you can make the distance longer, then that works really great. Same thing is true like for a wrench. If you have a nut that you're trying to loosen and the thing won't loosen, if you haven't changed the tire on your car, you're going to discover this in the rain one day, perhaps. That's very exciting. But if you have some kind of a wrench, I'll draw a lame looking wrench. If you have a wrench that's on that nut and you're trying to turn it and it won't turn because it's rusty or it's a lot of friction, it's really stiff. Well, you want to get the longest wrench you can possibly get, and you want to push way out here. Same principle. So the longer you can push, the further away from that nut you can push, the better. And you can even put a pipe on the outside of this and extend it, and now put your push out here, and then it might actually break. And so maybe you have some sense of that. Well, that's what's tipping the wall over. Does that make sense? So let's take a look at this picture. So I'm not going to go into it, but this is a house I designed. I'm taking all of this from a house I designed not too long ago. And this is what the engineer sent for the design of the wall. So I'm not going to take the time to go into what the rebar is doing and all that, because this isn't an engineering class. But I want you to notice this footing down here. Notice 2 feet 4 inches from here to here. So that's 28 inches. 2 feet is 4 inches, and then 4 more is 28. And that's the distance to what this engineer called the toe. And then there's 8 inches for the wall. And then there's 1'4", which is 16 inches for the heel. And so notice it says basement. So this is the basement of the house. That's where the people are going to be. And this is a retaining wall. This is all the dirt's outside here, kind of pushing on that. So does it make sense it wants to tip over? Well, here's what I just drew for you a second ago. Does it make sense? This is what, if the engineer does his job or her job and puts a bunch of rebar in here so that those two items, this is called the stem wall or just the wall. And this is the footing. If the engineer does his job, the footing doesn't stay behind while the wall tips over. Does that make sense? That would be bad. And that could happen, right? Does it make sense that wants to happen? For those of you who have some mechanical knowledge, you might stare at this vertical rebar now and notice, where is the rebar in the wall? The engineer said, put the rebar in the wall. Did you say put it in there anywhere?
What's 2 inches from the outside or the inside? Sorry.
Yeah, notice it's 8-inch wall, and he said put it 2 inch. And I'm saying he because it's a friend of mine that's an engineer here, but it's 2 inches. Like you put it on the back side of the wall. Maybe you can see why now. Does it make sense that won't happen if there's rebar connecting here? It'd have to like tear the rebar in half. So, okay, if he does his job, then that sticks together. But does it make sense in order for the wall to tip, it's going to tip up on its toe? Maybe now you can see why it's called a toe and a heel, because doesn't it sort of feel like a shoe, like your foot? That's what happens in your foot. So in order for that to tip, the question is, will there be enough torque? Will there be enough torque to get that to happen? Well, can you picture then that you really have here a certain force here? I'm just going to make some numbers up, but let's say that's 100 pounds. And as you go shallower in the soil, maybe this goes down to 80 and then it goes down to 60. But does it make sense every one of those has its own distance? So 60 is not near as heavy, but it's got a much longer distance. Down here, let's say this is 120 pounds. That's a really heavy push. 120 pounds is a lot of push, but notice the distance is really short. Can you see integrals happening here? How many force times distances do I have? How many arrows are there?
An infinite amount.
I mean, it's solid dirt. Does that make sense? It's not like there's just one arrow every foot. It's solid dirt. You've got, as Connor said, an infinite amount of these. So I'm going to have to add them all up in order to get the amount of force that's actually desiring to tip that wall over. And can you see just from the quick pictures that I showed you, there is a lot of money at stake with this stuff. And there's people's homes and apartment buildings, and people can die because they're standing there when it goes and so forth. It's like there's a lot at stake here, which is part of the reason. At least there's some fields where it's really obvious why you have to take calculus. If you're going to be an engineer, I'm showing you why an engineer would need to know calculus. If you're going to be a dentist, you also have to take calculus. Do you really need calculus as a dentist? I don't really see why. Don't understand that. So I gave you kind of a bit of an explanation here about some of the acronyms that are involved, but notice PSF, pounds per square foot, and EFF, effective fluid pressure. I stole this from my engineering friend because I don't understand any of this at all. Dirt is considered to weigh 120 pounds per cubic foot. So I've got 1 foot by 1 foot by 1 foot. You think about shoveling that out of the ground. That actually feels about right to me. I've shoveled, and if you have a shovel full of dirt, which is far less than a cubic foot, it's hard to lift. So an entire cubic foot being basically unliftable, 120 pounds, you probably aren't going to be able to lift that off the ground. That's quite a bit. But my engineer friend tells me 40 pounds per square foot effective fluid pressure. Let's see that I don't even have the right, it's supposed to be a P. In other words, dirt is not as malleable as water. So does it make sense dirt isn't going to, if you have downward pressure of dirt thanks to gravity, does it make sense it's not going to transfer into horizontal pressure quite as easily? There's going to be friction in it, so to speak. And so it's like 1/3. It's not near as, it doesn't act quite as much like water. With respect to water, then the weight would be the weight. Anyway, I don't want to bore you with the details because we're not all going to be engineers here. But moment is the engineering word for torque. There is a subtle distinction, but again, this isn't an engineering class. So I'm going to be using the word moment rather than torque because that's what engineers use. And all that means is the desire something has to rotate. And then I told you that. So let's take a look at this page and we're going to kind of do this together. So I simplified this by taking the footing out. Since the wall was 8 feet tall and the footing was 1 foot tall, that total wall is 9 feet high. And so what I want to do kind of with you actually, rather than, I am going to give you credit for this, but you don't know any of this stuff. So I can't just say, okay, go calculate the moment on this, but I want to help you formulate the integral for this because it's kind of cool. So be doing this with me to whatever extent you can, and let's try to get it done in class today. So does it make sense if you look at this house that I have drawn over here, that, you know, that here you can see the retaining wall running over here, and here's all the dirt piled up against it. This is when it happens, when you have a daylight basement house. And so from the back side of the house, it looks like a 1-story house, but because you're building on a hill, it makes sense for the bottom to be daylighted out. So you actually have a 2-story house, but you build it into the hill. And so this is where it happens. And you can appreciate what I don't want to happen here is for this dirt to tip this wall over and tip the house with it. I can't let that happen. And so in my case, when I draw a plan like this, I actually have to send it off to an engineer to engineer the wall, because he's got both more knowledge than I have about it. But more importantly, he has the engineer's stamp and the liability insurance, so that if this does go wrong, then there's actually insurance money that can pay the poor people that, you know, trusted me and the engineer to design their house, right? That's how the world works. So what we're looking at is just a 1 foot slice of this house, because does it make sense? Every single foot would be exactly the same. So if we can sort of get 1 foot of the wall not to tip over, then the entire wall won't tip over. So what we'd like to do is calculate what engineers call the overturning moment. How badly does this wall want to tip over thanks to the stack of dirt that you put up against it? And again, I've drawn all those arrows representing the continuous load. 40 pounds per square foot. Really, that's the number we're looking at. And since we're only 1 foot deep, you could actually think of this as 40 pounds per lineal foot as you go down the wall. So what that means is if you come down the wall 1 foot, then that's 40. If you come down the wall 2 feet, that's 80. If you come down the wall 3 feet, then that's 120. Does that make sense? So let's just make not an integral, but a rough, kind of do a rough problem. So would you agree that 40 is, well, if I came down 1 foot, isn't that 8 feet from the bottom? So the rough moment would be equal to 40 pounds. Notice the units of this. 40 pounds times 8 feet. So that's how much moment there would be right here. Now notice we skipped all of this in between because right here halfway, wouldn't that be 20 pounds? And I just ignored that. So this isn't the right answer, but it's an approximation. Plus 80 pounds, but notice I had to move a foot deeper. So now that's only 7 feet. And then I move a foot deeper, now I'm at 120, and now I'm at 6 feet. And so on and so forth, all the way down to, let's see, where would that be? 40 more, this is 160. Well, I'm gonna screw this up because I'm not sure I even drew the right number of arrows. 1, 2, 3, 4. Yeah, I think I actually did. Anyway, I'll just say dot, dot, dot. Do you agree that'd be an approximation? Now, here's where calculus comes in. How are we going to do this infinite? How are we going to have infinitely many of these?
Sum them all up.
Say that again.
Sum them all up.
Yeah. Now I'm not going to actually be able to do that because there's so many of them. But the problem is that to get it exact or accurate, I'm going to need an integral because I'm going to have infinitely many of them. But the question is, how are you going to do that?
This may sound crazy, but when we first started calculus and we used Riemann sums for, I feel like, problems similar to this, didn't we build an equation with the Riemann sum?
Yeah, that's kind of exactly what it comes down to. The problem is here, Eve, you're exactly right, is we need some kind of an equation because I can't write infinitely many of these down. And so one option would be to say, well, how deep is this? Like a second ago, I'll just call this X. Maybe I'll call it Y since it's vertical. Yeah, I'll call it Y. Does it make sense if I just pick this location right here? And of course, I need to let that slide everywhere. Does it make sense that is effectively that Y is kind of this number right here? That's my height. So sometimes it'll be 7, sometimes it'll be 8, sometimes it'll be 6. But even more than that, it's not just going to be 7 and 6. It's going to be 6 and 6.1 and 6.2 and 6.3. Does that make sense? But the problem is, what am I going to do for this? How am I going to get how many pounds that is? If I'm Y feet up from the bottom, how do I know what that depth is or what that weight is? Do you see what I'm saying? The question is, how many pounds is that right there? How am I going to figure that out?
I don't know if this is an oversimplification, but couldn't you make essentially just a linear equation out of the, you said it was linear growth, right?
Yeah,
Of the weight?
that's right.
Just make a straight linear equation using the 40 pounds and then integrate like on the y-axis essentially.
That's exactly right. In other words, if it's 40 pounds per foot, didn't we take 40 to get this? Didn't we go 40 times 2 and this was 40 times 3 because it was 3 feet down? So you're really taking 40 times however far down you are. Well, how far down are we? Does it make sense?
Or Y
That's
far
how
down.
far we are down? What am I going to call that?
You're gonna call that Y.
dy.
Y far down.
No, we already used Y. If I called Y the distance off the bottom, in other words, I'm treating this like the ground.
Is it D for distance?
So it is a Y value.
Isn't it a dy?
No, dy is infinitely tiny.
Oh.
Is it D for distance?
You could do
Would
that.
it be
for sure.
9 minus y?
The easiest way to say it is what Caesar just said. In other words, since this overall height right here is 9, then if I called this distance down here y, then this would be 9 minus y. That's the easiest way to say it. Now, again, we could define y to be whatever we want. I don't want to confuse you, but I could have said the distance down is y. And then that would have meant the distance from the bottom is 9 minus y. Like you can define y to be whatever distance you want. I was sort of calling this the ground. And so I said, okay, that's the distance up from there is y. So yeah, the growth is linear. If you're 2 feet down, it's 80. If you're 3 feet down, it's 120. You're really just taking 40 times however deep it is. Well, if we agree then that this is the depth, then isn't our depth 40 times however deep you are? So that's your depth, or that's your weight, or your force. And then times however deep you are, which is actually y. That's your distance. The distance from the toe, the point where it's going to rotate.
Hey Doug, quick question.
Go ahead.
Are you gonna post these notes,
Yes.
like with all the other notes? Okay, good.
Yep. Frankly, I'm doing this with you, for you, because I want you to see this example. I can't turn you loose on this, right? I mean, that's not fair. I'm going to turn you loose on another part of this in just a minute. But you can do this with me right now. But yeah, I'll post this. So the reason I think this is really cool is like this I think you can appreciate both because somebody would get paid to know this, but this is what real integrals look like. Because no one's going to give you an integral and say, can you take this integral? You got to make it for yourself. And so what values can y take on? In other words, what's the limits of integration here? What can y be?
0 to 9.
0 to 9. Because I can be all the way down at the bottom where y is 0, and I can be all the way at the top where y is 9. And so this is everything from 9 to 0. And I'm not going to go into units here, but I'm going to throw dy on the end. dy is a little bit of y, which is also in feet. So this, just to say this out loud, this is feet, this is feet. 9 minus y is feet. And 40, remember, is pounds per square foot. So 40 pounds per square foot times feet, times feet, times feet. That's going to end up feet times pounds in units, which is what torque is a force times the distance. It's pounds times feet. So we just made the integral. Now that's a very takeable integral, so take it. Don't cheat on this one just for practice. You don't need to cheat here because you can actually multiply this all out. But would an engineer cheat? Absolutely. Just type it in your calculator or type it in Desmos because you don't want to get this wrong. When you get an answer, blurt it out and let's just all agree on the right answer to this question.
Got 40 times the integral of 9y squared over 2 minus y cubed over 3.
And then plug 9 and 0 in and blurt out the numerical answer to this.
I got 4,860. And that would be pounds per feet squared, right?
4,000. I'm just writing down what he said. I'm not saying it's right yet. I don't know. That is actually foot pounds
Foot pounds. Okay.
because it's.
I got the same answer.
Yeah, me too.
Okay, so 3 people got it, so I think that's the right answer. So make sure you get that. And then just to highlight this a little bit in terms of units, like what is dy really? Well, does it make sense you just take a little stripe of dirt here, like a skinny little stripe of dirt, and that dirt is 40 pounds per square foot, and then the height of that is really teeny. It's a little teeny bit of y, because I can't make that really wide, because then I don't know what to call the distance. So it's got to be really teeny, and then, you know, times this distance right here. So it's kind of like the area of that slice of dirt right there times the fact that dirt weighs 40 pounds times the distance that it is. Now, of course, as a non-engineer, and as I've never seen this application before, that number doesn't mean much to you. Like if it had been 40,000, 480,000, you know, it's like, I mean, how badly does that want to tip over? Just a number. But the important thing is that number represents, as I said, the desire the wall has to tip over. That's what torque means. That's how badly, well, in the example that I mentioned before with the little box that I drew up here, maybe I erased it, you know, how badly does the box want to tip over if you push on it? An engineer's job is to not let stuff tip over. And I'm right after your class today, I'm teaching statics, and it's called statics because we would really like that wall to stay static, which means not move. So that sounds complicated. But this is exactly the math that I'm teaching that class. And that's why you have to take calculus where you're at before you go take engineering. Because in statics, we're going to think you know what integrals are, because you're going to have problems exactly like this in a statics class. Some of you told me at the start of this class, that's why you're in here, is because you're going into engineering. So cool. That's how badly it wants to tip over. Well, so what's going to keep that from tipping over? Like that's going to tip over. Do you see what I'm saying? Like that thing's tipping over. How are you going to stop that from tipping over? It wants to tip it over. And we now put a number to it. Well, in the case of just a wall, did you notice like some of the walls that I just showed you online, there was nothing on top of it. It was just like a street up there. So it's like, what's there to keep that thing from tipping over? Well, you got to tie it back into the hill. In other words, does it make sense you could put a bolt in this that was tied back into the hill and have some kind of a big like metal plate on it that would have to be pulled through the dirt to tip it over? It's like you can put things back in the hill that keep that from wanting to tip over. That's if there's nothing behind it. But in our case, and so calculus part of this problem is over. In a sense, I did it with you / for you, just because I want you to see how integrals show up in the real world. But here's what's gonna, and this I'm gonna get you started on this. This is not a calculus problem. This is just basic math. But can you see that there's a house sitting on top of that same wall we were just discussing? Can you see that there's a roof here and it has weight, right? Just because of the lumber that it's made of and maybe the snow that's on it and so forth. Does it make sense that that weight right there, whatever that weight is transferred down the wall all the way down here, and it sits on top of the footing? Can you see that that's pushing back? Can you see that, if you will, is trying to get this to rotate the other way? Can you see that that's pushing against it? Can you see that the weight of the house is going to keep that from wanting to tip up? Can you see that if this dirt wants to tip that wall over, when you look at the larger picture, it's going to have to lift the entire house up now. The wall's not just sitting there all by itself. It's got a house sitting on top of it. It's got a bunch of weight sitting on top of it. In a simpler example, if you're looking at this picture right here, Does it make sense if you kind of enlisted the finger of God to kind of push against that, that would push it right back down again? I mean, that's what the house is. The house is weight, and it's pushing against that, so it's not going to lift up. And so we just got to put enough weight there. Now, what I'm showing you is exactly what the engineer gave me. Like, I gave him the design, told him the wall was going to be 9 foot tall. And this literally is the design that the engineer came up with. And that's what we're going to analyze is his design. How did he come up with that? Why did he choose that toe to be 2 feet 4? Why is that so big? Well, can you appreciate with this finger of God, if you will, or the weight of the house pushing down on it? Does it make sense? The longer you make that distance right there, the more torque that weight of the house pushing down on is gonna give us. Can you see the house is trying to get it to push back and rotate the other direction? It's resisting the desire that wall has to lift up off the ground. And so the biggest thing the engineer can do is make that distance right there is kind of as big as possible. Now, you don't want to make it so big you cost the people building the house a bunch of money, but that's why that toe is so long, because we're getting a lot more torque out of whatever the weight of the roof is, for instance. We're getting a lot more torque by increasing that distance down there. So let's do this first one together, and then you can finish this chart yourself. So I kind of made a chart here just to organize yourself. Notice all the things that the house has weight. And it's in order. There's a roof pushing down. Ching. This wall right here that's on the outside of the house has weight. This floor right here has got weight that's pushing back. This pile of dirt that's sitting out there on the heel, does it make sense? That's also pushing back. And then this concrete stem wall right here, does it make sense? That's pushing back against that. All of those things are to the left of the toe. And so they're all pushing down, trying to resist. And that's why this is called resisting moment. That's what the engineers call it anyway. They're resisting. They're putting pressure on the heel to keep that from lifting up. And then lastly, just the footing itself. Like if this footing right here has weight, does it make sense it's not going to want to lift? So all of those things, what you're going to do is calculate the moment or the torque for each one of those. So you got to find the force and you got to find its distance from the toe. So let's do that together for the roof. So I told you this over on the side over here, but roof load, and again, these are real numbers. This is what I use to design houses every day. This roof has live load and dead load. What would live load? Why would they use the word live? What's live load?
Is that if there's like snow resting on top or something?
Snow is a great example of live load because it comes and goes. It's alive. It could be there one day, not the other. So can you count on snow to push back? Can we count on that? No, can't count on live load because it comes and goes. So you're never going to be paying attention to live load. Now here where we live, that 25 pounds per square foot of live load is based on how much snow we get here. But I'm designing a house right now that's up by Mount Ashland. Can you appreciate that number's higher? It's 80 pounds per square foot up there, live load. And I have to consider that because that can break the house. Does that make sense? I got to use larger lumber and so forth and bigger beams. So that live load is a thing when it comes to the house breaking, but it doesn't help me as far as this problem because it, you know, in the summertime, there's no snow even up on Mount Ashland. So you got to ignore all of those. What we're looking for is things that are dead load. They're always there. Like what would constitute dead load on a roof? What's load that's up there that never goes away?
Shingles.
Yeah, the shingles on the roof. And even that board, like the shingles are up here on top of this, but even that board itself. And so the weight of wood plus shingles, again, engineers have played around with this. I don't know where they got that number. 15 pounds per square foot of dead load. So looking down at the roof, they're saying 1 foot of roof between the wood that's up there, 1 square foot of roof between the wood that's up there and the shingles. That weighs about 15 pounds. That sounds reasonable.
Do the nails make any difference in weight, or are they so small that it's negligible?
That could be factored into that. Yeah, because you got to, shoot all those in. And of course, there's different kinds of roofing, like tile roofing weighs a lot more than just the regular shingles that are on most people's houses. So that's the rough number that gets used. That's probably a little on the safe side. In your house, if you just have lumber and the flat shingles, it probably weighs less than that. It's probably not quite that high. I know they have to beef that number up if you're going to do tile roof, but that's not that common.
Or metal roof too.
Yeah, metal roof. There's all kinds of roofs. So let's actually do the math on this. So it's now very important. I said over here, 1 foot section of the house. Remember, we're doing this all just for 1 foot of the house. If we can get that 1 foot not to tip, then none of the feet will tip. Do you understand how we're simplifying that? So we have a 1 foot slice of this house. So how many square feet is that? Since the weight is 15 pounds per square foot, then how many square feet of roof are up here? Well, notice that number right there tells you the answer to that question. Can you appreciate that this half of the house over here is resting on this wall? So that isn't going to help me. But this half over here, which is 13 feet, that 13 feet is over there. Now, in terms of engineering, you actually are looking at the horizontal version of this, just to keep it simple. Although this angle is actually a hypotenuse, it's actually longer than that. Does that make sense?
Yeah. I was about to say something. I was about to ask about.
Yeah, me too. I'm like, wouldn't it be longer?
Yeah. Now it kind of has to do with gravity too, because so anyway, let's just keep it simple for now. And then the other thing on this particular house is notice the 13 feet stops right there. Do you notice the wall has a little bit of overhang right there? Does that count or not? What do you think?
Yes.
It does. And so because we'll say this house, because this is what they usually are, we'll say that's a foot of overhang. Then we're going to say this is 14 feet long. And so it's 14 feet long and 1 foot wide. So does it make sense we have 14 square feet? So the square feet would cancel. So if I take 15 times 14, I get 210 pounds. Well, that's my first force, 210 pounds. Just for that 1 foot. Now, if you notice where that roof is attached, it's actually sitting on the outside wall, the outside of that wall right there. And so if you follow that all the way down, that's where that 210 pounds is acting, is right there on the outside of that wall. Does it make sense that this is its distance from the toe? And again, do you see why that's so important? Because it's not just force, it's also distance. So the engineer spec'd this out, and those are the same measurements the engineer had on the footing and the stem wall that I showed you a minute ago. How far is that away?
28 inches.
And notice you got to learn how to read dimensions here. So notice the arrowheads. See how there's an arrowhead right here and an arrowhead right here. They're saying that distance between this point and this point is 28 inches. So it's more than that. It's 28 from there to there. And then from here to here, the thickness of that wall up there is 8 inches. So it's actually 28 plus 8. Do you see that? There wasn't room for the 8 to fit inside there. So it's actually 28 plus 8, which is 36. So the distance is 36 inches. That's how far it is from the toe. So it's a force times the distance. Notice this is not integrals because there's not infinitely many of them. There's a finite list. This is a Riemann sum. What is there? 7, 6. There's 6 different parts of this house that we're going to have to find the moments for and add them all up. They're all different. This isn't a calculus problem. Calculus comes up when you have infinitely many forces at infinitely many distances. Notice it says feet though, because it's got to be foot-pounds. So I can't put 36 here. Do you understand that? That would not work. That'd be terrible. That's the kind of thing that would ruin your house like this. You're going to really screw this up if you don't put feet here. Now you're lucky in this case.
Yeah, I was going to say it's exactly 3 feet.
Because it's exactly 3 feet, but that's not going to happen all the way down. So I got 36 inches divided by 12. And so it's really 3. And now I can go 210 times 3, 210 times 3. Why am I using a calculator? I can do that in my head. That's 630. The units are up here, so I don't need to write them again. Does that make sense? That's why I'm not writing them. So there's 630. Hey, look, we're on our way to defeating 4860. Do you agree with that? Do you agree we need more resistance? When we add all these up, we better get more than 4860. Now, again, I paid an engineer $2,000 to design this. And so we're going to get a number more than 4860 here. What I'd like you to think about is how much more do you think it'll be? Think it'll be 4890, 5,000. So what I want you to do, and ideally before class is even over, so that you can check this. This isn't due until, Sunday, I think. So don't turn this in wrong. Like, check with me. Hey, I got this for an answer. Just keep going. Now, I told you where these things are acting. The wall is acting at its center. So I said the roof is acting at the outside wall. So that's why I drew the arrow at the outside wall. But the wall is acting at the center of the wall. So in other words, the wall is going to be acting right there in the center of the wall. Does that make sense? So that's going to make its distance shorter than 3 feet. Notice I told you the wall is 8 pounds per square foot of dead load. How come there's no live load for the wall?
Nothing will sit on a wall because it's standing vertically.
Yeah, nothing's going to come and go on a wall. A picture frame is like irrelevant small, right? A bird turd lands on it. Nothing that happens to a wall is really going to increase its weight much. So there really doesn't have a live load to it. Notice
Unless
floors
garage.
though, floor load has live load and dead load. Floors have a ton of live load because you can put, water beds and fill them full of people and stuff like that. But again, you're not paying attention to live loads. I just put them in there because it's kind of cool. But just to stare at a couple things, notice this floor, the floor lands on a wall inside there. So does it make sense that only half of that 18 is going to be floor because since there was an interior wall in this house, I'm not going to have, the same 26 up here. It's not going to be 13 feet. Do you see why it's half? If you have a whole bunch of weight on this floor joist right here, does it make sense? This half all goes to that wall over there. And this half goes to that wall over there. So for the sake of the floor, you're going to have 9 feet, just like we had half of 26 feet a minute ago. Now you're going to have half of 18.
Did you say that the wall was a foot?
Yeah, we're thinking of it as just a foot. Now the wall itself is 6 inches wide, but we're thinking of it as a foot deep.
So Doug, I'm not quite understanding why the distance from toe will be anything different than 3 feet.
Well, look at this wall. If we say that this wall, the weight of the wall is actually acting at the center of the wall here, since the wall is 6 inches wide, does it make sense that arrow down here is going to be right there, which is 3 inches closer to the toe?
Oh, okay. But in terms of like the floor, the floor won't have that issue. It'll be 3 feet up for like the floor.
No, because the floor Like if there's a person standing right here, notice there's nothing below them. In other words, this is the downstairs down here and people are standing down here. This is like an open room all the way across here. So if you got this person standing here that's got weight on him, does it make sense their weight ends up transferred over to here? So all of that weight from this half over, all of that weight ends up over here from the floor on top of that wall. So it all gets transferred over.
Yeah, but that doesn't get transferred over in the middle like the wall does.
It does, because it's going to land, it's going to sit on top of this wall. That wall is 8 inches wide, we're told right here. So that load is going to sit in the middle of that 8-inch wall.
So why didn't we do the same thing for the roof then?
Well, it's just because of the way the roof is actually attached. Do you see how it's attached?
Oh yeah, I forgot about that.
Rafter actually kind of sits on the outside of the wall.
For a second there, I did wonder why you mentioned the 1 foot overhang, but okay, cool.
Again, this is just cool. I just want you to understand like how the world works. There's people out making a living right now. I mean, I look at this kind of stuff and I think, God, that is cool. I mean, there's people that make all these calculations. It's like the people I'm drawing house plans for are all excited, like, oh my God, I got to build my own house. This is really cool. And, you know, my engineering friend is making all these calculations, and it's the difference between their awesome dream and their home in the hill and everything is all exciting versus it coming down. The very first house I ever worked on when I was fresh out of college, the entire 6,000 square foot house started sliding down the hill. I was just thinking, I'm so glad that that is not my fault, that I'm not the one that has to like fix this. It was an endodontist in Eugene, and you know, they built their dream home over the top of this pond, and they're all excited and spend all this money and $1 million house, and then it starts going sliding toward the pond. It was horrifying to watch. It was like every day you go out there, the crack in it would be a little bit bigger, and so it was just slowly sliding down the hill.
Is the weight of the center wall 48 pounds?
The center wall, I don't know what you mean.
The wall that's on top of the concrete?
No, because how tall is it? It's 8 pounds per square foot.
Right, times 12.
Precisely.
Okay.
So that wall is 96 pounds. And remember, that's 12 feet tall and 1 foot deep. We don't see the 1 foot deep. So it's a 12 square foot stripe of wall times 8 pounds per square feet. That's 96 pounds. So that wall weighs 96 pounds.
I have a question about the distance from toe for the wall.
Mm-hmm.
So the wall is 6 inches, which is sitting on top of the concrete stem wall.
Yep.
And so the distance there, instead of being the full 8 there, is that going to be perfectly half?
Yeah, generally speaking, and we are splitting hairs a little bit here, but generally speaking, anytime you have the weight of something, it's all going to concentrate to the center. So that's why I'm saying, because this is a 6-inch wall, that 96 pounds that we just calculated is going to be sitting right in the center of that, and that's going to transfer all the way down. So since it's in the center, that means this side is 3 inches and that side is 3 inches. So it's basically 3 inches closer to the toe than the roof was. So what did you all get for the distance then?
The distance for the wall, I got 2 feet 8 inches.
Say again?
2 feet 8 inches.
Yes, except for you want to be able to multiply it. So you're better off to say, well, it's 3 inches smaller than 36. And if I divide that by 12, I get 2.75 because you can't multiply by 2 feet 8. And that's actually 2 feet 9, not 2 feet 8.
I also got 32 because we're cutting that 8 in half, right?
No, it's 6 because that's a 6-inch wall.
Oh, I did a mistake on that then. Okay.
Now, when you get down to the concrete stem wall, that concrete stem wall is wider. It's 8 inches. Again, these are the actual dimensions. I could have made this problem a little simpler, but I'm giving you the actual dimensions of the real house. This side view that you have, that section view right there that you have, is from the house plan that I drew. So since we all did this one together anyway, if I take 96 times 2.75, I get 264. So now we're up to almost 900 on our way to 4,800. We're on our way up to 900. So this is what the engineer would have done. Engineers make like, I don't know, $100,000 a year.
For the weight of the stem wall, would it be 180 times 8 and then multiplied by, because it's 8 inches, is that a 16-inch wall?
Yeah, so the weight, notice you're told here that concrete weighs 150, not 180, 150 pounds per cubic foot.
Yeah, so you'd multiply that by 8, and then that's going to be per cubic foot. And since it's 16 inches, I'm going to do 16 divided by 12 and multiply that by my answer.
Where are you getting 16 from?
8 times 8, because it's 18 inches, or 8 plus 8.
So this stem wall is going to act right in the middle of this wall, which is 8 inches. So that means this distance is 4. So you're 4 to there, and then you still have 28 to go. I'm not sure I'm answering your question though.
I'm still confused. I don't know what I'm doing.
So first it's weight. If concrete weighs 150 pounds per cubic foot, that's what the PCF acronym is for, pounds per cubic foot. Then in order to get pounds, does it make sense I'm going to have to multiply by cubic feet? So what's the dimension of that wall? Well, it's 8 inches wide. It's 8 feet tall. And again, it's 1 foot back into the building. So the little block of concrete that's sitting there is 8 inches by 8 feet by 1 foot. So you've got to make cubic feet out of that so that you can multiply it by 150.
Okay.
Even though this is a calculus, and that's one reason I'm giving you this question, even though this is a calculus class, basic math is actually pretty hard in context. And it's the units that can actually help you know what to do. So my stem wall is 8 feet by 8 inches. That's not good that that's 8 inches by 1 foot. So I'm really happy with those foot dimensions, but I'm not happy with 8 inches dimensions. And you know the volume of a block, length times width times height. I need to multiply those, but they've all got to be in feet in order for me to get cubic feet.
So Doug, out of curiosity, oops, sorry.
Go ahead, Connor, and then
Oh.
whoever else.
Okay. I was wondering, do you see a lot of different variations? So like if you hired another engineer to do this exact same thing,
Mhm.
would he maybe, so like I'm on the soil center right now,
Mhm.
and for distance away from toe, I could go all the way to the end and play it safe, or I could like kind of put it right in the middle, it seems, and play it a little less safe, but it would maybe cost less money to put it in the middle. It seems like there's room for like your own personal like level
There
of safety.
totally is, and you're exactly right. My guess is, and I'm saying guess because I don't hire 3 engineers to do the same job, but if you gave this to 3 engineers, I bet you'd get 3 different answers. And they are, of course, CYA covering their ass. They're covering their rear end a little bit, and rightly so, because we don't want this to fall down, and they don't want to go out of business. But again, it is important with respect to what we're doing. It's from the center. In other words, I said the soil is centered. In other words, that's mathematically correct. If you think of this chunk of soil right here, there's that chunk of soil is 8 feet tall. It's 1 foot 4 inches wide, and it's a foot deep, but that's going to act at its center. That's where it's going to act. You can't put all of that weight at the outside end. That's actually not true, Connor. Does that make sense?
Yeah, but if we put it all on the outside end, wouldn't it be like a real sturdy, like way sturdier than it needs to be?
Yeah, well, it's actually, you're sort of lying because this inner part of the dirt is closer in. If you wanted to be safe about this, you'd put the entire weight on the inside edge where you're decreasing the distance a lot. That's the safer thing to do. If you put it on the outside, that's kind of dangerous because a whole bunch of that dirt isn't on the outside.
I gotcha.
So is the moment for the stem wall 2133.33?
Yes, it is.
Okay, cool. This is actually not very hard.
Once you get the feel of it, it's not. This is just basic math, but it's tied to a context that you've never seen before. And that's one of the reasons why I think this is such a neat problem, because this is the only way math, all of the math you've ever learned in your life, this is the only way it will ever come up. It will just be design this wall so it doesn't tip over. And when you say, okay, you don't even know what that might entail. And obviously in this world, there's a lot to learn in terms of like what's dead load, what's live load. I'm just giving you a little, an introduction to one place in the world where it's kind of cool. Once you get the hang of it, this stuff is really fast. This really makes all kinds of sense.
I definitely do not have the hang of it yet.
Yeah.
I was wondering if I could check a couple answers.
Yeah.
So for the floor, I got 4 says 90, and then 2.75 for the distance from toe.
That's a little too big, but it's really close. Practically speaking, that would be just fine, but the floor is sitting on an 8-inch wall. Do you agree with that, Alicia?
Yeah.
And therefore that weight, whatever that floor is, you're correct that it was 90 pounds, is going to act right in the center of that.
Oh, so then it'll be, I thought that, oh, it's going to be 32 over 12.
There you go.
So it's 2.667.
That's better.
Okay, and then for the soil center for the force, is that 960?
The weight of the soil?
Yeah, the pounds.
No. So look at the dimensions here. It's 16 inches wide. So the soil is sitting out there on the heel, and I'm told here that that's 16 inches wide. So that chunk of soil out there is 16 inches wide. It's 8 feet tall, and it's 1 foot thick. And soil is lighter than concrete. It weighs 120 pounds per cubic foot.
Okay.
And notice there's more soil out here, but does it make sense that isn't helping you because it's not sitting on anything that's going to keep the wall from tipping over? So it's only the part that's out there sitting actually on the heel. And so again, it's an advantage for an engineer to say, well, then let's make that heel bigger because now there's more dirt sitting on it. So that's one option they have. And I didn't understand this until I started asking him questions because this is pretty recent. This house, this is only a year old. I figured this out 1 year ago. So you could actually have a pretty short toe and have a gigantic heel sticking out there. And now you got thousands of pounds of dirt out there pushing down on it, keeping it from lifting up in the air. And so that's a solution too. So the question I asked him was, how did you know to just pick 28 for the toe and 16 for the heel? And he just told me, it's just kind of experience. But you'll be surprised in a minute how over designed this is when you actually get the answer. We only need 4,860 foot-pounds of resistance here to fix it, and you're going to get a number significantly larger than that.
Well, that's a good thing.
And of course, yeah, you want there to be a factor of safety built in.
So I got 800 pounds for the stem wall.
That's correct.
Is that, oh, okay.
Yep. So let me say something about this, just because I would assume, I mean, you're welcome to stay as long as you want and finish this whole thing sitting right in front of me right now. If you have the time, good for you, do it. But you might need to leave, and it's like, 8 minutes after class. Extra credit down here. It turns out that engineers design a factor of safety into this, and that factor of safety for a house or for something like for just one person, if you will, is 1.5 times. In other words, if this has 4,860 foot-pounds of desire to tip over, then you want the resistance to that to be not just equal 4,860, but 50% higher than that, because you want a factor of safety built into this, obviously. But you don't want the factor of safety to be like 10. You don't want it to be 4,000 or 48,000, because that's costing people a lot of money. So they actually calc this in. So when I asked my friend the question, like, how do you know what those distances are? Basically, he just picks them randomly, and then he does the calculations we're doing and then goes, oh, look, it works. But this extra credit question is to go back and say, well, he picked 28 inches for the toe kind of randomly. But what if you didn't pick that? Because it turns out it's way over designed here. What if you made it shorter? What you don't want to do is redo all these calculations with 28 being, say, I don't know, I guess I'll try 26. And now you got to redo the whole thing again. So the extra credit is, could you actually set that distance from 28 to X? If you leave the heel alone, could you set that distance to X and actually figure out what that would be, so that your answer is actually 1.5 times bigger? If I take 4860 times 1.5, I get 7290. So this would be a good answer for the resisting moment. Since the overturning moment of 4860, if I multiply it by 1.5, I get 7290. So that would be a good design. Make it safe, but not way over. And you're going to get an answer right now in your calculation. You're going to get an answer higher than that. Like, he way over designed this. That costs people money. Like, people have to build this stuff. They have to pay for concrete. Concrete costs $120 a cubic yard. He's costing people money by his calculation, but nobody knows enough math to question him. So whatever he specs, people are just going to do it. And you obviously want some safety built in, but you're going to get a number higher than 7290 for your answer right here. So my question is, could you actually save the customer some money and design it a little better? I got the impression that he didn't do that, or, you know, didn't know how to do that, because he told me he guessed. He guessed at the size of the footing because he has experience. And then he made all these calculations and was like, oh, cool, it worked. And then he's done. Notice I said extra credit, which is code for don't do it.
Hey, Doug, all right.
It's not terribly hard, actually. It's a wonderful problem, but yeah, go ahead.
The stem wall was 800, but I'm getting like thousands, like 3,000.
So tell me what you did.
So
You're talking about the force, not the moment for the stem wall, right?
no, I'm talking about the moment. The moment is, oh, okay. No, I'm talking about the moment.
Okay. Yeah, you are going to get thousands for this.
Okay, cool.
I was asked for the weight, and
Sorry, I misheard.
yep, no worries.
Yeah, I didn't realize how over-designed he made this until that moment.
Yeah, the soil should be even more than that, correct?
The soil almost does it all by itself.
Right. Yeah, that's what I was seeing.
Okay, so I'm just trying to get all my answers right here.
Yeah.
The floor weight, I got 90, and the distance from toe is the 2.667. And then the moment was 240.03.
Yep, and you can just round that to 240.
And then for the soil, is the weight 1,280?
Yep.
280, okay.
I got a total resting moment of 8,147.97 feet-pounds.
That's not enough. You said 8,000 something?
Yeah,
That's not enough.
okay.
One of yours is wrong.
So for the distance from toe for the soil, is that 44 inches?
Yep.
Thanks for your help today, Doug.
Yeah.
So the distance from the toe floor, would that be 104 inches?
For what?
The distance from the toe on the floor, it would be half of that 18 feet plus another 4 inches, right?
No, because the entire floor, like this person standing on the floor right there, all of that weight ends up over here. The only place that weight exists is right there. Because there's nothing under it. In other words,
Okay.
this is all open.
Okay.
So no, you're way too huge.
Okay. No, yeah, it's more like 32.
Yeah. Do you see how the length of that toe has such a huge effect on what we're getting for moment?
Yes, I do.
So for the moment, for the soil, I got 4,693.33.
Correct.
And then for the moment for the stem wall, I got 2,133.6.
That's correct.
I'm not really understanding how to do the footing part though. I'm stuck on like, what is the dimensions of that, I guess?
So notice you have all the dimensions across the bottom here for how
Mhm.
long it is. You have the height of it right there, which is a foot.
Okay, so it all added together.
Yeah, you just got to add them up yourself.
Okay.
It's actually kind of interesting when you get down into the soil and the stem wall. It's like you look back at the house and go, whoa, the roof and the wall and the floor actually didn't contribute very much.
Okay, so now I have an answer of 9,427.97.
That's close enough. Something's a little off, but it's darn close. Tell me what you
Okay.
got for your distances.
I got 3 feet for the roof. The wall is 2.75. The floor is 2.667. The soil is 3.667. The stem wall is 2.667, and the footing is 2.667.
Your footing is too big. Your footing, the weight is right in the middle of that footing. How wide is the footing?
28 inches.
52.
No, the overall footing. How wide is
44
it? I'm sorry.
44 inches.
No, bigger than that.
52.
Because it's 28 and 16 and 8. The 8's in there too.
Oh, okay.
The dimension lines are hard to read because the numbers are so big, but it's 3 different sizes there all added together.
So for the footing force, I got 650.
True.
So for the distance from toe for the footing, that is 2.1667.
It's all true.
You said that was right?
Yeah, that's true.
Okay.
All true.
Okay, I think I'm done. I guess the last 2 things I want to confirm is the footing moment would be 1408.33 and the floor moment would be 240, right?
Both correct.
Awesome.
Nice job.
All right, so I have my total resisting moment. And for that, I got 9,369.29 foot-pounds.
That is correct.
Woo! That took me longer than I feel like it should.
That's what I'm saying. Practical math, even when it's somewhat easy, is not near as easy as it seems like it would be. It's interesting too, because you imagine like every single calculation you make here, every single button you push, every single dimension you stare at, like this person's house hangs in the balance. Hundreds of thousands of dollars and their dreams and all that stuff. What I've noticed about math in the real world is you don't need it very often, but when you do, you got to concentrate really hard for 1 hour and make a bunch of calculations. And then you go and act on those calculations with hundreds of hours and thousands of dollars. And so you just can't afford not to get it right. But the majority of the time is spent cutting rebar and, you know, putting forms there and so forth. I mean, it's kind of cool to watch people actually follow the design that you made and, you know, build it all and actually have the confidence that, you know, it's going to stand there. I just think it's so, I'm not an engineer, but I think it's so cool for an engineer to go out to a job and just see all these people pouring concrete and twisting rebar wire together and all of this stuff. And it's all based on a design that you made, and you're able to sort of certify, you know, you're the only one that understands the calculations well enough to kind of say, you know, I know this is actually going to work.